Okay, so let's talk about higher order astigmatism and field curvature and how they impact design of a mobile phone lens. All right, so to do that, I want to start off with some equations. This is how to describe to fifth order your S and T curves in your sagittal tangential field curves in your field curvature plot. Right, so this is field height or image height. This is your displacement of the focal position, ZT and ZS, or ZT and ZS as we say here in Canada. Um, and they're given by these equations. ZP is your Petzval surface, sort of like your natural image surface, because it's natural because if astigmatism is zero, then your T and S curves will coalesce onto the Petzval surface. And if the Petzval is zero, then you've got a flat surface. Right? If these coefficients are zero, it's flat. So what I want to do here is to mathematically understand why it is that when you've got higher order aberrations, or why is it that you can actually take your field curvature plots, your S and T curves, and change change them around, twist them around, and make them even intersect at places, right? Um, and I unfortunately I don't have a more complicated like seventh order or ninth order, but I've got it to fifth order here. So let's ask the question: what happens if I've got a flat Petzval curve where the coefficients P3 and P5 here are zero? And I'm able to get the Z and ZT and ZS, ZT, ZS curves to intersect at some field point, right? Where they intersect, would they necessarily intersect at the Petzval surface? To do that, you equate the ZT and ZS curves and do the algebra to solve for H, right? If you do this equality, then all your Petzval terms, they cancel, they go away. And then you do more algebra and solve for H. H is equal to the square root of this negative number. And it can be negative because if either A3 or A5 is negative, then you've got a square root of a positive number, right? So at this field height, it's saying at this field height, they intersect. So what is the displacement? What is the focal displacement across from the field when they intersect? Right? So you plug this h back into the previous equations, and you end up with this, where your zt equals zs, with the displacement equal to this magnitude, right? So what happens if you sketch this out? At h equals to this value, at a point at which a3 is positive and a5 is negative, um, your ZT and ZS is equal to this magnitude, and the curves will look something like this because you got a third order curve going like this, and then the fifth order curve bending it back, and then they intersect at this point here at the field. And because there is a magnitude to the displacement, a focal displacement, they are not necessarily at the Petzval surface. That's interesting. Okay, that's interesting. But if you extend them, one or them of them can intersect, right? So this is kind of what's happening in a mobile phone lens design, where you've got lots of aspheres, lots of wiggles, and therefore very, very high orders, higher than the fifth order, and you get your field curvature plus your S and T curves to kind of wiggle around and intersect, and you try to flatten where they intersect. And that's not really necessarily a flattened field; they're just intersecting there, right? Okay, but if the displacements, the deltas are not too high, then your MTF can be not too bad, right? That's the idea. Okay, so let's now let's go to mobile phone lenses. But before that, let's go back to first a singlet. This singlet, all right. In this singlet, it's from a lens that I designed as an exercise in a previous video. I think the video is called "Do aspheres correct the field curvature in a lens design?" If you have not seen that YouTube video yet, go there and see that and come back here. Basically, this is a singlet where I purposely make it biconvex, and I challenge that condition with an asphere. I challenged the asphere to correct the field curvature for a biconvex lens. And it ended up being this, using, I think, 5 terms with a Q-type asphere. 5 terms, I think it's 5 terms. And the field curvature plot is like this, and it's interesting to find out now what happens to the MTF versus field plot. So this is the MTF versus field plot. right? The tangential is here and the sagittal is here, and you can see there are wiggles. Each wiggle point correlates with where the field curvature wiggles. All right. Um, okay, so this is kind of what happens in a lot of mobile phone lenses. Not all, but in a lot, where you've got wiggly S and T curves, and you've got therefore wiggly MTF versus field curves. Okay, so let's go to an example actual mobile phone lens design patent. This patent is one that I discuss in my book, this book, right? In chapter 1, under the subsection title of um, why are mobile phone lenses not used as laser scan lenses? It's just a researchy type of question that I discuss. And then I discuss this lens, and I discuss some characteristics of this lens. You can, if you go to my website, you can find the link for my book. This book again, this book. Chapter 1 is the entire chapter 1 is available free to read online, or you can download it as a PDF. It's free. So just go there and look for this chapter for this lens. Look at the let's see if you can see the plot here. All right, look at the MTF versus field plot. There are a number of wiggles. And if you look at the field curvature plot, there are also a number of wiggles. It looks on average flat on a flat image plane, but the wiggles are quite non-negligible. The magnitude of the wiggle relative to the focal length of the lens is pretty big. And that's why when the field curvature plots wiggle, the MTF curves also wiggle. All right, and this happens very often. And you can see this lens has many terms up to the 16th order using an even asphere. Right? Okay. So great. So now I want to show how to reduce the number of wiggles, right? Even as you aspherize. So I'm not saying that we should not aspherize. We should. We have to aspherize, but it's just how you do it. So to do that, I'm going to show you the singlet meniscus spherical lens that I designed as an exercise in my previous YouTube video on do aspheres correct the field curvature of lens designs. So if you go back to the video, you'll see this. And let's see if I can explain things here. All right, so so I've got this lens, the singlet, and if you look at the field curvature plot, it's very flat. I have here the same scale as I did before for the previous singlet asphere, right? It's very flat because I zeroed down the Petzval sum, which is the third order Petzval field curvature. All right, so you end up with MTF curves. It's very smooth here, and of course, there's some residual astigmatism mid zone in the field because I did not correct that at that time. Okay, so one thing to notice is that the MTF curve, MTF versus field curve, the MTF is pretty low here, 38% compared to the singlet asphere previously that I showed. Right, that one on average it was pretty high, near 60%. Between 50 to 60% on average, but it's got lots of wiggles and lots of astigmatism. But it was on average pretty high. So now I'm going to show you how to increase this MTF with slight aspherizing because it's all about just spherical aberration. Now it's no longer about the field curvature. I mean, it's sort of, but not really. So let's aspherize. Let's go to even asphere. Even asphere, and again I'm going to pick up the second radius from the first, make it the same all the time. I'll put a variable on the first radius only. Stop shifting is the magic solution to astigmatism correction. I talk about it in chapter 1 of my book as well. Lens thickness, you need that as well, because it's all about where you put the rays from one surface to the next surface. They see a effective optical system there with its own EFL, and that's why you got distortion, right? Distortion basically is EFL versus field. All right, so I'm gonna put a variable on the fourth order term. Now, the thing is, I I interchange between doing this, and sometimes I put variables in the conic first and see if that's an improvement. If there is, then I add the fourth term and the sixth order term and so on and so forth because I'm adding perturbations. But in this particular case, I go straight to the fourth order term because I know I'm just correcting spherical aberration. Okay, so here in the merit function, if you can see that, let's see. Okay, in the merit function, I am going to delete the field curvature, the astigmatism correction merit operand that I had imposed earlier on, and I'm just going to tell the lens design to make the RMS wavefront error as good as you can for 3 field points. Let's use the 70% field. Okay. 1, 1, 1. There's a ladybug. There's a ladybug. Sure. Okay, I don't want to kill you. Okay, so okay, so what else do I have to do? Okay, I need to release this. Okay, release that. Okay, so I only have variables on the for the asphere on the fourth order term currently. Okay, so now let's optimize and see what happens. Hammer. I'm gonna hammer now. Okay, you don't see the pop-up screen, but it's actually doing it. Okay, and if you can see the curve, that's the curve. Okay, well, it goes up and down here. Okay, I did an earlier exercise before I did this, where I did not put the 0.7 field. So let's see. I want to show you this because I know I've done it before. So I practiced that just to check I get the right result. Interestingly, if I get a better curve, if put the half field point. So this is why you should always muck around, fool around with a merit function and see. Okay, so now again I'm gonna control the halfway point. It actually turns out to be better. Okay, so we'll optimize now. Okay, and what do I get? Okay, here we go. Oh, nice. Okay, do you see it? Yeah, you see it. Okay, I'm not blocking the view. Okay, so next I'm gonna add the sixth order term. As you can see, it's not a wild asphere. It's a pretty well-behaved asphere, right? Okay, now let's optimize with the sixth order term. Optimize now. It's turning, it's doing its thing. And now I've got, can you see that? Yeah, I'm not blocking the view. Okay, good. Now you've got this nice flat MTF versus field plot, right? Nice and flat. And the field curvature plot is also nice and very flat, very good. It's got a little bit of, displacement here, but it's still very good. So this is how you kind of patiently tweak the design from scratch until you add more spheres, and if you kind of know what you're doing, you can come up with a very nice monotonous curve for the MTF versus field plot here. And so as the last example of this, let me show you a mobile phone lens design exercise that I did a couple of months ago. Okay, it's coming up here. And what it is, okay, here, okay, so 2.4 millimeter focal length, 2 millimeter wide here, and 5 elements, some aspherizing, some conics. Look at the field curvature plot. It's got some high order terms to it because it wiggles a little bit. And then look at the MTF plot at 200 cycles per millimeter and at 100 cycles per millimeter is fairly smooth, right? Okay, so this is what I mean when I say that you can try to control your designs. Okay, it's just there's some trade-offs here, right? Manufacturability wise, not great in terms of the lens edges, but it's still something. Okay, and that's what I want to say. Thank you. Bye bye.